So I already know some of you here. I see a bunch of familiar faces from many different places, conferences or different companies or parachain teams or Parity and many other places. For those that have not met me before, haven't seen me anywhere, I am Maciej. This is how you pronounce my name, but don't worry, you can mispronounce it, I'll still get it. So I've been helping the PBA for quite a while, since the second one in Buenos Aires was always a student, and then I joined Parity right after, working on the core protocol and helping PBA ever since, slowly as a lecturer and taking more and more responsibilities and explaining the protocol more and more. So I am based in UK, so I've flown here yesterday very late night. I had exactly 0 hours of sleep, and I am incredibly jet lagged. So if I mistake anything or miss something, please ask questions. We have a lot of time. All day today, how many hours, 7 or 8, is just me talking. And tomorrow, pretty much the same. I think Filippo will be helping me with one lecture. So we have plenty of time to have discussions about any topics related to Polkadot, to the protocol, to how it operates, to the ecosystem, and anything surrounding it. It's quite impossible to cover everything, so there are no dumb questions. I purposely left some things open so you guys can ask, and I will go in details and explain, or link you to some resources, give you some guides, or chat after the lecture. Okay, I think those were the disclaimers, and now we can slowly get into it. Maybe a tiny bit more of what I'm actually doing at Parity other than the PBA stuff. So my main responsibility at Parity is working in a team called Parachains. This is essentially the team that's responsible for the deep protocol stuff of Polkadot that makes it work, that makes it be a sharded network that combines all the different rollups, all the different shards, all the different parts of Polkadot, and that can do it safely in a resilient way and still be efficient. This is a bit of a jargony answer, but I will be slowly unpacking what it all means so you actually get what I'm working on. Okay, then. So I think you had some introductions. Actually, how many of you have completed the online version of the PBA before? Like, raise your hand. A pretty good amount. So some of you probably, I mean, most of you probably seen me there at the end explaining some of the stuff I will be explaining here. Hopefully, I'll be going into more details. And if you have any questions coming from the PBAX, also a good time to voice them here. So through the PBAX and through the lectures you guys had yesterday, I think you already have some preconception of what a blockchain is. At least a pretty simple one of a state transition function with some state, and it's slowly changing every single block. And the main purpose of my lectures today and tomorrow will be to explain how we went from this simple view of a blockchain, something like Bitcoin or Ethereum 1.0, to something more Polkadot-like, something different. And just to be clear, this image is not just a random artistic version. This image kind of makes sense once you understand Polkadot, and hopefully by the end of all my lectures, you will look at this image and kind of get what is happening here. But Polkadot is more than a blockchain. Yes, I will be primarily explaining the protocol stuff, how it operates, the details, the Polkadot SDK, but it's a bit more than that, and I think it's a good time at the introduction at the beginning to mention all of that other stuff. So it is more than a blockchain, it's also the ecosystem and all the motivations of why we are building what we are building. Because we are not building it to actually be, I don't know, beautiful. We're building it for a specific purpose. It's not a protocol for the sake of a protocol. So one of the main ideas is that we want a system that relies less on trust and more on truth. We want to eliminate intermediaries. We want to eliminate potential entities, companies, governments that maybe do not betray your trust today, but they have the ability to do it in the future, even not intentionally, maybe accidentally. And Polkadot in this case tries to be this trustless computing infrastructure, a platform for builders and developers to build stuff that is not as easily, cannot be as easily manipulated. So now let's take a look at what I have prepared for you. This is the specific agenda for this lecture now, and later on, at the end of this lecture, I will show you the agenda for the next 2 days in more detail. So first, we'll be looking at some of the core values of Polkadot, exactly what it stands for, some of the tenets. I see some people here with the Jump t-shirt, so I think some of those tenets will be very, very familiar because I'll be heavily inspired mentioning the Jump tenets, which we'll get to later on. But then I'll also try and explain the overall current modern blockchain architecture landscape of different competitive networks and ecosystem, and where exactly Polkadot lies in comparison to them. What is different? What is the same? What are we evolving? What are we adapting? What are we parting ways with? I'll try and summarize some of the key decisions, like the key type 1 decisions that are very difficult to change, that are defining what Polkadot is today, and will probably be defining what Polkadot will be in the future. And then, just for the sake of organizational housekeeping, on every single of my lectures, there will be different actors I will be talking about. For instance, maybe this lecture will only be relevant to validators. Maybe this lecture will only be relevant to nominators, just so you know who are the actors we are talking about. I also have a short glossary of all the tech items, the different frameworks, and different pieces of tech that are core to what Polkadot is today. So then you can either Google them yourself or ask me questions. And later on today, I think, there will be a workshop where I'll be essentially showing you some of those repos, some of those tools, and walking you through them. And then hopefully you will also download, install, and play with them yourself. And then finally, we'll be just going through all the different things I will be covering in the next 2 days. And actually, another small disclaimer. So this whole Polkadot module, for all the previous PBAs, it was always designed to be at the end of the PBA. It was the crown jewel. After you learned all the other stuff, you had the Polkadot module bringing it all together. This time around, we're doing it slightly differently. We're starting with Polkadot. We're telling you the high-level picture of what it is, and then we're zooming in to different smaller sections. So again, if there's anything that doesn't make sense yet, first of all, ask a question. Possible answer will be, you'll learn about it in 2 lectures from now on. It might happen, but I'll still give you at least like a TLDR, a short version, a short answer, so we know what to expect. But please ask the questions. Like, I really, really mean it. Raise your hand and ask questions. Okay, so let's look at some of the core tenets. So, even though Polkadot is changing over the years, and trust me, it has changed a lot since the original white paper vision. We had the Polkadot 1.0, which was how Gavin wrote it initially. Nowadays, we are more in the Polkadot 2.0 age with things like, maybe they will not make sense to you, but give it some time, agile core time, asynchronous backing. This is the 2.0 era, and we're slowly heading towards the 3.0 era with things like Jam that are changing the picture quite a lot. But nevertheless, if it's the 1.0, 2.0, or 3.0 version, those tenets are quite stable and relevant to every single iteration of the protocol. This is what we are building the protocol for. It has to have those properties. So first one is that Polkadot needs to be accessible. It shouldn't be a permission system. It's a permissionless system for a reason. This is how we give this accessibility trait to the users. There should be negligible barriers to innovation. It should be something you can easily build. You don't need to have some kind of government-issued ID. You don't need to be particularly wealthy to play with it. You don't need to be a reputable person. There are some things that might be gated, but generally the whole platform should be available to people. And hopefully, like, this is already quite obvious to you guys because you are all sitting in this room, which was completely founded and funded financially by the OpenGov project. We are trying to spread the access to this knowledge as wide as possible. This is what the ecosystem does. It tries to make it as accessible to the people as possible. And next one is generality. So generality is very connected to Polkadot being this ubiquitous computer. So every single computer needs some kind of programmability, needs to be general purpose. And the first iteration of Bitcoin and the current iteration of Bitcoin are not particularly general. They're doing a very, very specific thing. And this was the biggest advancement of Ethereum. It actually pushed the generality of the whole ecosystem, of the whole blockchain. And this is also a trait that is absolutely core to Polkadot. We need to have this programmable logic in the system. The next one is composability, which can be very closely married with interoperability. So in Polkadot, and we'll be diving into that in a second, there will be different parts of the state, different shards of the computation. Think of them as like different cores on a CPU. And there needs to be a method that those cores can sometimes communicate, maybe some external registers that they can call into. This analogy to a computer is there for a reason, a very specific one. But composability and interoperability essentially forces us to give those tools to developers that allow all those different shards of different cores to communicate and be at least somewhat coherent. And also this property is very often abandoned or completely misunderstood and not prioritized enough in other ecosystems. They're focusing a lot on scalability. They have some generality and accessibility, but they often forego any sort of interoperability by default. They essentially throw out all the responsibility of building it to the users, to the developers, instead of providing the tool set from the get-go. And the next two ones are performance and resilience. So we care about performance. I think it's pretty obvious that if we have this general compute platform, it needs to be performant. It needs to allow for more and more computation to be held. We all want a bigger variety of applications, and for variety, we need throughput, not just financial applications. So just like Web2 systems needs to scale their architecture, we had to evolve and innovate our architecture. We need to essentially move away from the system of, one core per machine. We need to move into this threaded, sharded mindset where things can be executed in parallel. No longer it is feasible for every single validator to validate every single transaction when you scale to this height, when you scale to this size. And this is why Polkadot will be using state and execution sharding to essentially make it so we are much more efficient with how we compute, but still preserve that resilience. Because it's very easy to scale performance while foregoing resilience. And that's why I didn't even put them as two separate slides, because those two are really, really closely married together. And it's, yet again, very easy to forget about resilience and just do performance and essentially pretend like you're scaling, pretend like you're achieving your goals. But one cannot go without the other if we actually are building something that should last. And do notice that decentralization is not one of the core tenets here. Decentralization is actually not the most primitive thing we are going for. It is very important, but decentralization is just a means to an end. It's a means to be resilient. We are decentralized only to achieve the resiliency that we desire. So there is not a single point of failure through a centralized entity that can essentially betray our trust. Okay, so any questions so far? Question to the left.
So hi, can you hear me? Yeah, hi, Spen. So in in regards to the core tenants, which is the most challenging as transition from 1.0 to 2.0 to 3.0 to keep as a core feature of Polkadot?
I think it's definitely the performance and resilience one. I think generality has been, I wouldn't say mastered. There are things that can be improved, but it's not at odds with the other tenets. Like you can pretty safely improve generality without sacrificing the other ones. The problem with performance and resistance and resilience is that I think it will be in one of the slides later. You know, the trilemma in blockchain, resilience, performance. Like it's very difficult to improve one without sacrificing the others. Accessibility could be better, for sure. But accessibility is one where I feel like there was barely any progress, not in Polkadot, in the whole Web3 space for many years in the past. You either require a lot of stake to participate, and it hasn't changed. There was no major innovation in this department. Hopefully there is some major innovation coming to that. I think the proof of personhood projects that are being worked on in Polkadot essentially try to challenge this accessibility tenet, which was completely surrendered by the ecosystem. So maybe this one is the hardest because there was no progress in it, so we barely even talk about it. Any other questions? Question?
Thank you. How do you measure specifically performance and resilience? I mean, how do you know you already achieved a vision for specifically resilience? I think it's harder.
So it's an active area of research. I don't think you can achieve it. There is not a magical number you meet and then, okay, we won. That's it. We are done. It's definitely a scale. It can just get better and better. And for instance, resilience, there's a price for it. If we want to scale resilience, maybe the whole system gets more expensive. So it's a trade-off. I think there is a place for project and ecosystem in the world that are not as resilient, but maybe are cheaper. It's essentially a good that comes with a quality. And some people prefer a very high quality decentralized compute. Others, for some smaller computation, can settle on a lower resilience, cheaper compute. So it's a matter of essentially what's the ratio between your performance and resilience, how cost effective you are. And this is quite difficult to measure. When it comes to resilience, Nakamoto coefficient is one of the things you can look at. It's not perfect, there are some downsides, but at least it's giving you some good of a picture. It's, for those that don't know, it's essentially a coefficient that tries to encapsulate in a single number how decentralized an ecosystem is when it comes to its validators, how difficult it is to corrupt it, how many different nodes, how many different entities you have to attack to maybe get control over the network. This is how you can encapsulate at least one part of the resilience. When it comes to the performance, it's really difficult. One thing you can look at is TPS, like transactions per second. But this is a very inconsistent metric that you can very easily gain. Based on if you batch transactions, there is not a common standard for what a transaction is. Are you sending transactions that reap the account, like delete it after you send? Do you do a keep alive transfer that sends from A to B but keeps both accounts alive? Those metrics, like those two settings, very vastly change what TPS you will get on a network, and there is no standard on it. So if you see a chain saying, hey, we do this TPS, I'm not saying it's bullshit, but you really have to look into it to figure out, okay, what are they actually doing? There's a really good talk about TPS from Sean. I will link on the Discord, or maybe Sean will link it. I'm sure he has it available somewhere. That I really, really, really highly recommend you to watch, so you can be demystified about the whole TPS scaling misinformation that is out there. Question next to you, and then we'll go to the ones in the back.
How do you measure Nakamoto coefficient?
Can you go again?
How do you measure Nakamoto coefficient?
What's the Nakamoto coefficient for Polkadot?
No, how do you actually measure it? Because I saw the stats online and I don't really understand how they are measured.
I don't remember the exact formula from the top of my head. I don't think it's particularly complicated. We can take a look at that after this lecture.
Wait, I know. Is the mic working? The Nakamoto coefficient, you basically count validators until the minimum number of validators you need to have 33% of the stake. That's Nakamoto coefficient, right? So like if you have a system where the top three, like there's like 100 validators and there's 3 validators at the top who each have 10%, the Nakamoto coefficient would be like 4, right? It's just those top guys can collude and basically control 33% of the stake. If you have it really well distributed, then it's about like 1/3 of the validators. So Polkadot has a really well distributed staking. So you have 300 validators. So we get a coefficient around 100, right? That's but it's basically, it's about which is the smallest group we can create, which owns 33% of the stake.
So how you calculate it will depend on the network. There is not a single magical formula where you can plug it into anything. But yeah, right now in Polkadot, I think we're actively raising the number, but I think it's like 600 validators, and we're approaching 1,000 as our stable amount, active at a single time. We have more potential validators. We'll get into that in the next lecture. But for a specific 24-hour period, we are narrowing it down to like 600 to 1,000 validators. And this is how many you would have to attack and potentially take control of. Okay, questions in the back or to the side, and then we'll slowly walk to the back.
Hi, I'm Shagun. So when we talk about interoperability, is there such a thing that between parachains, which are like connected to the relay chain, there's like more interoperability, and it gets hit when we talk about monolithic chains built using substrate? So is it true that there will be like less interoperability between parachains and monolithic blockchains built using substrate, and more interoperability between parachains?
Just to make sure I got the question right. So yes, I'm mostly, when I say interoperability here, I mostly mean XCM between parachains, so how they communicate on substrate chains. You cannot use XCM between non-parachain substrate chains. If you have a substrate solo chain and different substrate solo chain, XCM is not something that you're really sensibly able to use. Monolithic block, it doesn't even make sense to talk about XCM and interoperability when it comes to monolithic blockchain, something like Bitcoin, because you need to have it built from scratch every single time. If you want to build a bridge between something like ETH 1.0 and, I don't know, Bitcoin or something, it's a bespoke project every single time, tailored to every single chain. So yes, if you are using substrate, and you connect to the Polkadot relay chain, you just get it out of the box, and you don't have to really do much with it. I hope it at least partially answers your question.
Yeah, and what about like chains built using substrate, but the chains which are like solo chains?
So for those, I don't think you get much benefits from XCM out of the box, because the relay chain is essentially a relay chain that passes over your XCM messages. Like, we'll be going into XCM in like future lectures and weeks. And so I'm sure this will be answered in detail practically. But generally speaking, out of the box, if you have a substrate solo chain, XCM is not part of the scope. Like, it's not immediately available to you. You can interpret XCM messages, but there is no scaffolding that passes over the XCM messages. There's no XCMP, XCM protocol.
Thank you.
Okay, more questions in the back? Okay, have a mic.
Yeah, besides light clients, what other efforts are there to make Polkadot much more accessible, not just to developers, but also just Web2 consumers?
So what other efforts are there to make it more accessible? Is that correct?
Yeah, besides light clients.
So first of all, I think the proof of personhood is one, as I mentioned. Right now, Polkadot is OpenGov and stuff like that requires you to have a lot of stake. Proof of personhood potentially opens the door to a mechanism where it doesn't matter how much stake you have, maybe one person, one vote. And this is not perfect for every single type of a vote, but there are some types of votes where this would be really, really useful. So that's one of the things. And the other stuff is, this is also going a bit ahead of ourselves, but building a parachain, building a shard of Polkadot, like a Polkadot rollup, is not easy. It's pretty difficult to do. Like, it's still much, much, much easier than building like an Ethereum rollup, but it's still a bit of effort. There are initiatives, and I will be also showing that on the workshop later on, I think, where you can essentially do one-click deployment of a Polkadot rollup to essentially eliminate those barriers and make it more accessible. So you no longer have to immediately spin up your own infrastructure, RPCs, and all the nodes. This can be provided to you at the beginning, and then you can slowly decentralize it and move it out so it's easier. There's the introduction of smart contracts, because not everyone wants to be a substrate palette developer. If you just want to code in Solidity, it's available. It makes the whole platform more accessible. So I think there are many, many, many different avenues to continue pushing the accessibility agenda for Polkadot, but also on a larger Web3 scale to innovate accessibility, which I think is the proof of personhood stuff.
Cool, thanks.
Any question where there's a hand?
Who has a mic? Hi, Mike. My name is Suraj. I wanted to ask, like, as Polkadot is layer 0 and most of the blockchains are layer 1. So if can you give me some insights of synchronous composability and how that is like, because if we consider layer 0, then Polkadot will be inherently asynchronous, right?
So synchronous composability is difficult. It's really, really difficult. And again, those are really good questions, but kind of getting ahead of ourselves, because we're talking like in-depth XCM properties, in-depth interoperability properties. So when people say synchronous composability, they, for instance, mean a smart contract calling a different smart contract, and this one calls a different one, all in a single-ish state transition in a single block, for instance. This is very easy to do in a monolithic blockchain. This is pretty difficult to do in a sharded blockchain, where potentially your different smart contracts might live on different shards. So XCM doesn't immediately allow you to do synchronous composability. There is a bit of a delay between sending your message and it being received on a different chain. There are some things coming in the future, like Jam, that might help with the synchronous composability stuff. How helpful it will be is, I think, up for debate, and it's still an active development front.
Thank you.
Okay,
Yeah. Hi, good morning. So Krishna here. We mentioned that like we had around 600 validators right now. So around like 600 validators right now that are like validating, and we are planning to have around 1,000. So when we talk about the number of validators, are those like run by Polkadot, or majority of them run by Polkadot clustered, or like how are they working?
so the next lecture is titled Staking, and I will be going in depth into that one. So I will just pause it for now, because I think it will just be answered. It will be all about this specific question.
Thank you.
Any final? Okay, last question for now. To the left, if there's a mic. But a short TLDR, no, we are not controlling all 600 validators. It's not sitting in our basement of Parity or something. They're properly decentralized, and I'll explain how.
Value resilience more than decentralization. It seems weird to me that having decentralization would be the only way to just achieve resilience, especially when you also value performance. Like in other systems, you would just have like replicas, or like why is decentralization the only solution?
It's definitely not the only solution. It's for sure not sufficient. It is required, but not sufficient to achieve resilience. I think you can build some systems that are resilient to some degree, but in the end, if there's a single party holding the keys, or holding the software, or holding the hardware, like this party controls the situation. So like this decentralization is not here because it's not enough. If you're just decentralized, I don't know, in hardware, but then there's like a single person that controls all the knowledge of the protocol, you are not decentralized. So this is just a convenient way of achieving resilience. Like, can you think of a system that you think is resilient but is not decentralized? Because I think this is the actual problem. Like, if you can come up with a system that is not decentralized but is resilient, then like pitch it. This is amazing. And I think there are possible ways you can maybe achieve it with like trusted execution environments, but they still have a pretty long way to go to be that safe and that secure. If you would have this magical execution box, then yeah, I think you could sensibly achieve it without decentralization. But the current world we live in, simply the practical reality is that it's very, very, very difficult to achieve any sort of resilience without decentralization. Okay. Final question.
Where?
Hello.
Here, I think there's a mic already there. If it's working.
Hi, I'm Lynette. My question is, so one of the limitations of legacy blockchains that I know Polkadot is trying to solve is there no customization. So the one size fits all architecture, right? So when you say generality, what exactly do you mean by that as a core tenet?
By that, I mean things like having the ability to write smart contracts with custom logic. By that, I mean creating palettes with custom business logic for your parachain. This is essentially diving into a few of the slides I'll have in like 10 minutes. So I think your question will be answered in a moment, but smart contracts, customizable palettes, non-heterogeneous chains. So essentially every single shard of Polkadot can have different business logic, different computation. They're not just copies of the same shard. This was the approach of Ethereum when it was moving towards the scaling solution to just have more copies of Ethereum. This is not what Polkadot is doing. Polkadot is allowing fully customizable business logic shards that are not copies of each other. So we are pushing the generality a bit further. But this can take many different forms based on what different level of the stack you are. For just a smart contract dev, having access to smart contracts is already giving you generality. But on many different levels, we can provide higher levels of generality. Okay. If there are any questions, leave them for a second, and I'll get to them after we go through a few slides. So hopefully that will also answer some of your questions. So I'll give you a quick explainer of the current blockchain landscape. What is there and how Polkadot actually compares to it. And see different solutions, and then we can maybe appreciate some of the decisions we made. So we started with single, simple state machine blockchains like Bitcoin. Every node in Bitcoin had to fully sync up with the state of the whole network. All of the nodes had to fully re-execute every single transaction in the network. So it didn't really require much hardware at the beginning because the state transition in something like Bitcoin was trivially simple. There wasn't a generic computation. It was just a simple transfer of balances from A to B. Not much complexity or generality there. So the state transition function, which is what business logic the blockchain has, was pretty much immutable. Bitcoin just sends balances. That's it. It doesn't really do much more than that. So absolutely no generality here. It does a very specific thing and nothing more than that. And I often hear this critique that blockchains, maybe not critique, but a description, that blockchains are just this giant decentralized ledger that holds your balance. And it certainly was true. It was true for something like Bitcoin, but it really isn't true for modern blockchains, for things that are pushing to something bigger than that. For instance, how Ethereum did it. So the decentralized ledger, very accurate for Bitcoin, very inaccurate for Ethereum, very inaccurate for Polkadot. Because the big innovation was that it is programmable. The state transition is no longer fixed. It's no longer the same. It can be actually edited. It can be changed. So it's much more about the computation, this custom computation we are doing in every state transition, rather than just holding the balance. And it's also opened a lot more demand for the block space, for the computation that the blockchain is actually securing. Because it's not just balances moving from A to B, it's just some computation being secured, being verified by the network. But even though we had this programmability, it was still using the simple approach of just a bunch of nodes all living together in a single cluster where everyone re-executes everything. There was more demand, but it wasn't met with any new scaling solution. It was just, oh yeah, everyone still does it. We have much more computation, but the system was the same. The security system guarantees were exactly the same, and they simply didn't scale to this new demand. So then there came solutions that tried to quickly boost the throughput, to essentially allow for this higher demand to be feasible, at least potentially feasible in a short term. And the easiest solution to achieve that was to just throw more money at it, have bigger hardware, have bigger computers, have bigger validators. But if the hardware gets super beefy and super expensive and no one can afford it, your network stops looking like this and just starts looking like that. And it just leads to very strong centralization where validators are controlled by a very small minority of entities, people, or companies. So topologically, it's much different. It's no longer this decentralized network. You're kind of achieving your throughput goal, but by sacrificing a lot of the decentralization, which sacrifices a lot of the resilience, which is what we truly care about. So some people didn't like that, and they actually tried to innovate. We started having solutions like Cosmos. Who here has played around or know what Cosmos is? Cool. So Cosmos was one of the first to essentially create a system where no longer every single node re-executes everything. There are essentially smaller islands of state. And then there is some communication mechanism between those islands, but there isn't a common ground where they all meet. It's separate islands with their own separate schemes, separate security guarantees, some of them more secure than others, and then some potentially bespoke communication between the islands. It was definitely reacting to the need that, well, it all cannot be re-executed with everyone. There has to be something has to give. We have to separate our responsibilities. And finally, we can take a look at how Polkadot compares to those approaches. So Polkadot, since day one of its inception, was centered around this sharding idea, this splitting of states, splitting of execution, to essentially allow for this higher throughput. A single monolithic blockchain absolutely cannot scale unless it compromises on core blockchain principles like resilience by sacrificing decentralization. So this is the triangle I was talking about that you will see in a second about scalability, security, and decentralization. Something has to give at one point. So on a higher level, Polkadot also decided, just like Cosmos, to split its state into smaller subnetworks, to split its re-execution into smaller subnetworks. But this is where the comparison ends, because it did more than that. It essentially, and also each subnetwork had its own fully programmable runtime logic. This is the state transition. thanks to Substrate, which we'll be learning about next week. But then instead of fully separating the execution and security layers, Polkadot instead chooses to start pooling some of them together. They essentially combine forces between the different islands. And there is a cross-section that combines all the different small islands, a meeting point for all of them. The islands are no longer fully separated with very faint and barely functioning bridges. There is something in between making them all come together. They have something in common. And the more and more subnetworks we add, this emergent behavior, the existence of the central core becomes more and more transparent. So if we crystallize it a tiny bit, some nodes remain unique and specialized for the different smaller islands, the custom business logic execution of an individual shard, while other nodes remain at the core. They are essentially the bridge, the security layer that combines and allows the other smaller islands to communicate and work together. And the universal nodes in the middle will be the unifying force, bringing all of the different subnetworks into a single cohesive structure. We'll be probably the next 2 days primarily spending our time looking at those two different groups of nodes, how they operate, what do they do, what types of responsibilities they have, what types of potential punishments they might be open to. And probably some of you already know what I'm referring to, but the central core is essentially the relay chain. This is the beacon chain that's all the different parachains, aka small shards, aka that Polkadot rollups are connecting to. And looking at this diagram, I think it should already be pretty straightforward, like where the Polkadot logo is actually coming from. I guess it's just all the parachains pulling together. So if we summarize and zoom out for a second, Polkadot at its core is still a sharded network, but it's a sharded network with something in the middle that connects all of it and allows the system to still be somewhat coherent when it scales, instead of creating a million islands and every single island having to build their own custom bridge to every other island. The resources and the security is pooled, so they all benefit from the same security instead of every single one having to reinvent the wheel from scratch. So you can think of Polkadot's relay chain as this like layer 0 solution that essentially allows other chains to connect to it. It's this like mothership for other blockchains, for rollups. Any questions about this section? One question in the back.
I guess I'm wondering, is there a way that parachains just like break a specific palette to be their own islands? If a parachain decided to leave, instead of like cloning a solo chain repo, but how would they actually do that?
So the ecosystem gives you a pretty open way. If you start as a substrate solo chain, you need to provide your own security. You need to have some kind of a staking, proof of work, or whatever other mechanism that essentially protects you from Sybil attacks. If you have that, then you can very, very easily migrate to be a Polkadot parachain by using Cumulus, which essentially translates your substrate solo chain into a Polkadot parachain ready binary. The opposite way is a bit more difficult, because if you are a parachain, you are not the sole provider of your security. Your work is a bit simpler because you don't have to worry about proof of stake. You just inherit the security from the relay chain. So if you would like to separate, you essentially need to create it from scratch. You have to guarantee some security before you disconnect. So at the disconnection process, you're not vulnerable to an attack. So it's not that it's easier to connect than disconnect, but most that are connected are not responsible for their own security. You can have a parachain that has staking and has their own security, but it's not necessary when you're a parachain. If you are a parachain that has it, then the disconnecting step is quite easy. Question. If we have a mic to the front.
Hello, Marcin here. I have a question. Is it possible for parachain to, for example, disconnect and then reconnect again and retrieve its previous state from relay chain?
Yeah, for sure.
Okay, so the island can disappear, right? And then, for example, someone decides like, yeah, I will start again, and it will get the last state?
So I think next lecture is staking, and after that I'll be talking about pretty much this. Maybe not in a specific example of disconnecting and connecting and disconnecting, but I will be talking about the state, like where it lives. The short answer is the state of a parachain of a specific shard is pretty much fully maintained by the collator nodes, the nodes of a specific parachain. We only store the roots or the hashes of the state on the relay chain. So if a parachain disconnects, then before they disconnect, the collators were holding all the actual state. They disconnect, well, they still hold it. If they want to connect, well, they still hold it. They just have to resubmit the hash. What will potentially happen if they disconnect for too long is the relay chain will trim the hash of the state. So when the parachain reconnects again, they just have to provide it. So either we trust them, maybe they have some governance system to provide, hey, this is our current state root hash we decided on, this is what we are using.
And how long it takes before it gets trimmed? Because I don't know.
How long does it take for what?
How long does it holds before it's trimmed?
That's a good question. I don't know exactly. I don't think it will be, I don't know. I will have to speculate. I don't want to do it because then it's getting the recording, and if it's incorrect, it's incorrect. I can take a look, but I don't think it's particularly important because even if it gets trimmed, the collators are the arbiters of the actual state. If they disconnect it, I assume this was their OpenGov, their governance scheme decided to disconnect. So if their governance scheme decides to connect, there needs to be consensus they're connecting and with what hash of a state. So those two things should come together. And even if we trim it, like if this parachain as a sovereign entity decided to reconnect with this state, that's up to them. We don't control it. Because it's, from our perspective, it's not a state transition from the pre-disconnect state, from the post-disconnect state. It's just a new parachain coming in with some state. We don't care where it's coming from. They're a new joiner. Question? But I don't think this specific case like ever happened.
Hi, Luca here. So I have a question regarding trilemma. So we have scalability, decentralization, and security. So we can like define different from the relay chain and parachain, one without other can do. And like, where do we hit the maximum parachain number on the relay chain? How scalable is that actually?
So the limit is like a numbers discussion. We can have up to 1,000 validators, and we can have a parachain for every 5 validators. This is generally the limit. So we can go to up to 200-ish parachains. This gets a bit more complicated because it's not 200 parachains, it's 200 like Polkadot cores. And I'll be talking about what that means later. But for now, yeah, 200 parachains seems to be the current practical limitation of the system. We can maybe go a bit higher, like 250, 300, but then we are stretching it. But if we would really reach that limit, we have some ideas in our cookbook that could push it further. But those are pretty wild. Some of I think there are some blog posts about it from the Web3 Foundation researchers that if we ever would reach that limit, what we can do is we can create another relay chain that also has those 200 parachain slots. And then the relay chains all connect together. And it's like this cascade of networks. But we're not close to saturating like this is a lot of parachains. Like I think Ethereum has like maybe 10-ish rollups that like really have a lively ecosystem. 200 is a lot, like a lot.
Thank you.
Wherever there's a raised hand.
Hello. I think you say that if we build a parachain that connect to relay chain, we don't have to worry about the security because we share security to the relay chain, right? My question is, if we have so many parachain that secure by the relay chain, doesn't if the relay chain getting hacked, all the parachain will be also get hacked? So what I mean is, how if we add more parachain, does it also make the relay chain become stronger or anything else? Thank you.
So just to be precise, when I say the relay chain is a source of security, I don't mean that the parachain has nothing to do. Like they can still break things, but they can only break things for themselves. The security essentially comes from the parachain gives us the cookbook. They give us the recipe. They give us the state transition function. This is how they are defining how their own little blockchain, their own little parachain can transition from one state to the other, what is legal and what is not legal. And the relay chain is the arbiter that essentially looks at the cookbook and makes sure that this specific parachain makes state transitions that are legal within its confines from the cookbook they gave us. So if the team that's, harboring the parachain makes a very stupid cookbook that allows for some exploitation, but it's within their rules, the relay chain will be, sounds good to me, the cookbook allows it. So there are still very dumb things you can do as a parachain developer if you provide like misconfigured or not properly functioning cookbook, which is the runtime of your parachain. Just to be clear what I mean by security is given by the relay chain. This is essentially, the relay chain, you can think of it as an auditing scheme. Like all the parachains are their own little blockchains, and in the end, they're providing their blocks, they're providing their state transitions to the relay chain so it can audit that the state transitions are actually legal within their own defined rules. Question, all three.
Hi, I was wondering if it's possible that we can design a parachain to be to function itself like a mini relay chain with sub parachains with it as well for more scalability and layered security.
You definitely can do it. I don't think there's anything fundamentally stopping you from doing it. I think Hyperbridge is not doing exactly that, but it's essentially a co-processing parachain that allows you to verify some external computation and connect to some external, for instance, Ethereum chains and stuff like that. So you can definitely do it, but then you're limited to how much computation a parachain block can actually handle. You cannot connect, much more computation than the single parachain can handle, and you're limited on two things. You're limited on how much computation you do. There is a reference hardware for a validator, and you can only have up to 2 seconds of single-threaded computation for a single parachain block. And you're limited on something we called POV, proof of validity. Doesn't matter what exactly it is, but this is the I/O bandwidth, how much memory you're touching, inputting and outputting. So as long as you keep within the bounds of execution and I/O, then sure, you can do it, for sure.
Hello. So say that there's two parachains that want to communicate with each other, the relay chain would always be seen like as the middleman, kind of similar how in clustering the master-slave kind of architecture?
Not necessarily. So it is like that nowadays. I hope that this will be in-depth explained in the XEM lectures. I don't know if you have them. I think you have them next week, maybe, yeah, probably next week. Right now, we have something called essentially DMP and UMP, which is upwards messaging and downwards messaging. So the message goes from one parachain to relay chain into a queue, and then from the relay chain, it gets read in one of the parachains. And the messages are literally written on the relay chain. This doesn't have to be like that. And we already have a draft implementation and a draft improvement to this XCMP, which is the cross-chain messaging protocol, how we pass the messages around, that essentially instead of literally writing the full message to the relay chain, it only passes around the hashes of the messages, and the messages are passed off-chain, which is much more efficient and much better on every single front. It's just a bit of a pain to do, and there's a few other caveats, but this is something we're actively working on having. So the relay chain will still have an involvement in it. It's still this like authoritative thing when it comes to cross-chain messaging, but it's not as involved. And it's, just to be clear, it doesn't know what message is being passed. It simply sees it as an opaque blob. It doesn't know how to read it. It just passes the bytes around. It doesn't do any verification on the data. It's up to the parachains to decode it.
Thank you. Like I was wondering if we have any benchmark to compare between the performance of parachains in terms of like cross-chain communication and other like networks that do the same. Because I have other questions, but I'm guessing we will have another like lecture about the bridging things. So I will keep it for, okay.
Yeah, so there will be, I think, a full dedicated workshop and at least a few lectures just about XCM, the cross-chain messaging, by Cisco. I think he's on site already, so maybe you'll see him around. I don't know how much info there will be to compare messaging between ecosystems, because it's just really difficult to compare. Every single bridge works differently. Like in Polkadot, we have this, predefined bridging between all parachains given to you immediately. But how do you even compare it to something like Ethereum, where every single rollup in Ethereum has a different bridge and it doesn't really work the same way? It's super hard to compare. You would have to do a bespoke comparison for every single bridging solution. And then again, like, what is a bridge transaction? We go into this debate of what is a transaction, like what type of state you are touching. It's difficult to compare. But what I can definitely tell you is that the bridging speed, like the bridging throughput, is not the most important limitation right now in the ecosystem.
Internally, I mean like not internally between parachains, because I'm expecting it to be very fast, but I mean like between the parachain in Polkadot ecosystem and outside, for example, like from Bombium to Ethereum or whatever.
Mm-hmm. Is the question if you can or how efficiently can you do it? So it, yet again, very much depends on the specific bridge you're using. I think there is one of the students here that is working on Hyperbridge. He's there. I think he will be able to give you some numbers for how quickly you can do it using Hyperbridge. Something like Snowbridge will give you different numbers. Using, for instance, Snowbridge, which is the bridge between Ethereum and Polkadot, it's, the speed is different from Polkadot to Ethereum, then from Ethereum to Polkadot. It depends how quickly you can provide the finality proofs. So this is a very specific numbers discussion on very specific examples. It's borderline impossible to provide generic statements for that.
Hi, Chris A. Can you help me understand some of the trade-offs between something like layer 0, like a cross-chain messaging protocol, I guess, that's meant to allow interoperability between monolithic blockchains? But from what I understand, like you need a smart contract on the origin and the destination chain, and then they have some decentralized infrastructure in between that facilitates the message passing. But I guess I'm just curious about the different trade-offs and the pros and cons with Polkadot's architecture versus something like layer 0.
Wait, so the question is how the Polkadot's way of doing it compares to what?
I like layer 0, which is like a cross-chain messaging protocol.
Yeah, you can describe the current way Polkadot does it as a layer 0.
Okay.
I think the whole is it layer 0, is it layer 1 debate is a lot of terms that don't actually mean that much. Like, is Ethereum a layer 0 as well? Like, is Polkadot a layer 0? Is it layer 1? It doesn't really matter.
Oh, there's an actual company named Layer 0. Yeah, yeah. There's an actual company named Layer 0. Yeah,
This is an important bit
sorry,
of
that's the
information.
general term. The actual company Layer 0. Yeah.
Okay. Thank you for clarifying that.
Yes, sorry, I should have clarified that.
I don't exactly know what they're doing, so I don't think I can immediately.
Okay.
Yeah, probably question to them, or we can discuss it after the lecture, but I don't have like an immediate answer. Okay, let's do like one more question, and then we have to continue.
So one thing to add to his question, Layer 0 is a company that bridges networks with custodial wallets. And I guess that's not the way you do it in Polkadot. But my question is, like, what is a parachain in terms of like the relay chain, and how do I prevent DDoS attacks? Because in essence, I can spin up a very strong server that is a parachain and just spam your relay chain. So what's a parachain in terms of relay chain, and how do you prevent it?
So the relay chain makes very few assumptions about what a parachain is. Generally, there are sovereign blockchains. You can spin up a parachain that's just your laptop and connect to the Polkadot network. You can do it. Is it super secure? Probably not. It's partially up to the parachains to define exactly what is their infrastructure, who is running the collators, are they decentralized, what are the incentive schemes, do they have their own token? Like, what a parachain is super, super flexible. What a rollup is super flexible. When it comes to creating spare relay chains, you can also locally spin up a parachain and locally spin up a copy of a relay chain for testing purposes. Like, you will not get the same security of connecting to the actual relay chain of Polkadot and being audited by this decentralized network of validators, but you can do it.
So, but about the DDoS attack, so if I'm a legit parachain, I want to have the guarantee that there will be no downtimes, and my blocks will be added to the relay chain in a constant time. So if anybody can connect to the relay chain and everything can be a parachain, does it basically means that the legit parachains are under threat, that their processing time will be compensated potentially at some time?
So when it comes to DOS attacks, the relay chain provides security guarantees when it comes to the validity of the state transition. It doesn't immediately give you liveness guarantees. Liveness guarantees are essentially the responsibility of the collator networks. We have to depend that they still provide some parachain blocks, some state transitions. If you have a single collator running in your parachain network, probably your liveness is dependent on that single collator. If you have a scheme where you have a parachain, but the collation can be provided by pretty much anyone, there can just be a random node spawned and it gives you the collation to the relay chain validator. It could work and it could maintain liveness, but it's very much within the decision of how they implemented this specific parachain, like who can provide the collations, who can provide the parachain blocks to the relay chain. Okay.
I wanted to add something. Of course, like if you want to connect to Polkadot, you need to buy core time, so you need to spend dots. Then you have to pay for fees. Then you cannot really like stop the relay chain because, maybe correct me, you might say if I'm not correct, but you have still like within the relay chain blocks some like space or computation is dedicated to activities that are key for the ecosystem, for the relay chain and not the parachains. So you cannot really, I mean, you can do it, but yeah.
Hi, Nemanja. Does every parachain has its own sequencer, or you can use the validators as a like sequencer or something?
Very good question, which will be answered, but I will give you a sneak peek. Yes, every single parachain has their own sequencers, and AKA, when people say sequencers, this is just an Ethereum term that we call a collator. This is this specific parachain-specific rollup node. And yes, each parachain has their own collators/sequencers. There are some initiatives to make it very easy to spin up your sequencers or collators to start development, like Polkadot deployment portal, which, one-click deployment and you get some infra set up immediately, and then you can slowly either control and decentralize or do whatever with your collators later on. But I think as of today, there aren't really nodes that sequence or collate for multiple parachains at the same time. I think there are some attempts at it, there are some projects working in this direction, but I don't think this is really something that's being done today. Okay, one more question, and then we'll get to the rest later. Whoever is the closest. And the questions either will be answered later or there will be more time for questions.
Yeah, for those rollups that you showed, they're talking about doing layer 3s, which seems to be like what Polkadot does in layer 0. Is there, are they copying what Polkadot has already achieved by trying to do this with like the layer 3s?
Are you talking about the layer 0 company or the layer 0?
Oh, no. I mean like how like Arbitrum has this thing called orbit chains, which seems to be like similar, but they're already a layer 2, but they're trying to put this like layer 3, which is like a chain of chains. And Optimism has a super chains thing where anything that's based on the Optimism thing is connected with shared security and like messaging. Is that like anything inspired from Polkadot, or is it anything close to how they're doing it? Do you know about it, first of all?
So what I will say, I have a whole lecture answering this question. I will actually link it to you guys in the Discord to maybe at least cover some of the points, the questions you raised. But generally speaking, Polkadot made a lot of bets and decisions to have this chain of chains, layer 0 architecture. And initially Ethereum was completely no, like this is not how we are doing it. And it turns out after we've been doing that for like years and years, Ethereum is now like, yeah, that's actually a good idea, let's do it as well. And they also are going in this roll-up architecture, this sharding architecture that if you look closer into, it's super similar to what we are doing in Polkadot nowadays. We just call them parachains, they call them roll-ups. They have two main variants, optimistic roll-ups and ZK roll-ups. The way we do parachains is actually none of those two. It's a third option, which we sometimes call cynical roll-ups. It's a bit closer to optimistic, and I have a full lecture on it. There are some benefits, some downsides, but generally our cynical rollups are a bit more efficient and safer and more straightforward in how quickly you can communicate between chains and stuff like that. The latency on finality is much, much lower. But both Ethereum and other ecosystems seem to be converging on this design quite noticeably. If that at least partially answers your question.
Yeah, it was more of like from the Arbitrum layer going up, they have a layer 3, which is doing like the shared security model that is very similar to what I'm seeing in Polkadot. So just like wanting to know if the layer 3 idea is actually layer 0, but because they're layer 2, that's all they can do.
Yeah, I mean, it's layer X plus 1 minus 1. Like if it's 1 or 0, doesn't matter. It's like, is it layer above or layer below is what truly matters.
Thanks.
Okay, I will continue for now. If there are any questions, they will be addressed later. So to kind of continue this whole roll-up discussion we kind of started here is Ethereum is also doing the sharding architecture, the Ethereum 2.0. Hopefully you will see the slide in a second. But the thing is, even though they're doing it and they're having those super popular optimistic and ZK rollups. Vitalik, some time ago, I don't remember the exact date, published a rollup stage, like a rollup roadmap of when a rollup can reach its maturity. And if you actually look at the roadmap for most of the rollups, a big chunk of them is like stage 0. They're like super early level, not fully secure. They're running like most of them, and I was going into details for Arbitrum and all of them, they're running like permissions sequencers, a vast majority of them. The ZK ones, pretty much all of them are running fully centralized ZK provers. So they're still at a very, very early age of development. And I think they still have a pretty long way to reach good enough maturity. And I already kind of went and explained some of the comparisons between rollups, how we have them as parachains, and how Ethereum has the optimistic ZK, and how we have the cynical rollups, aka parachains. There's a bit of a delay on the slide, so you'll see that in a second. Okay. And if you would like to learn more about the comparison between optimistic rollups, ZK rollups, and parachains, aka cynical rollups, there's a lecture link I did recently on Web3 Summit. I will link it in Discord as well, because I don't think this specific link is in the slides you guys have, but I will link it. Or we can just discuss it later on, either on the breaks or future lectures. And to give even more stats about it, there were questions like how many rollups can we accommodate, how many rollups there are, stuff like that. In reality, like top 10 of the top 20, the 10 out of top 20 rollups are all powered by Polkadot. In our case, we just named them parachains, but it's literally the same idea, the same concept. And the whole idea being that it's much easier to develop, to spin up your own rollup, to spin up your own parachain on something like Polkadot with Substrate, with PDP, the Polkadot deployment portal, and with other stuff. And it comes with native bridging that you don't really have to work on to get going. Because first and foremost, the whole idea behind Polkadot, it is meant to be a platform for builders where it's easy to deploy that stuff. And Polkadot mission is just to provide this secure and scalable and resilient computation, this infrastructure for resilient compute to users. So what are some of the core decisions that are made in Polkadot, just so we can galvanize some of them? So the first one, as I mentioned, is sharding. This is the cornerstone of Polkadot. Polkadot was never meant to be this big monolithic chain. It has separate shards handling state and execution, and they all can execute in parallel, which actually gives us the performance we need. Each individual shard can be seen as an upchain when it has some programmable logic that can be modified and maybe custom business logic for your specific need. In our case, we are achieving that through programmable runtimes, which is essentially the cookbook I mentioned. This is the state transition function, which in the past was done through WASM, WebAssembly, but in future, we are slowly moving to a RISC-V alternative with Polkadot VM. So it's giving us much more control over how this VM executes the state transitions. It will potentially give us gas metering, which we didn't have in the past, and much better performance, which is also a big benefit. And funnily enough, continuing this analogy, Vitalik also announced they're probably moving EVM to RISC-V in the future. Well, we already have it. So it's yeah. So we already can play with PVM and RISC-V on Polkadot. And because you have this cookbook, you have this WASM, you have this runtime available for every single parachain, it allows you to do a really cool thing. Because if you have the rules, the business logic of a specific parachain, then you can also upgrade it into the future. You can essentially make changes to it in the future. You don't have to commit to the single business logic forever. It allows you to do something we call forkless upgrades, which is dynamic updates to your business logic without any risk of your chain forking and different paths disagreeing. I think this will be covered in more detail later, but this is a very convenient tool for parachain builders. It's essentially, adapting your cookbook after some time to accommodate for the new business logic you might need. And I think we already talked a bunch about interoperability, all the messaging that comes from XCM. So there's that. And there's the shared security aspect. All the different shards are essentially being protected by a single system. So every single parachain is as secure as the other ones. They're all atomically progressing forward. There isn't a situation where one island has a state transition and progresses while all the others remain. They're all essentially coming together and progressing together, and they can process messages between each other at the same time atomically. There are also the aspect of on-chain governance. I think there will be a full-on lecture or even a module, 1 or 2 days, where we'll be discussing governance in detail. And it will be pretty theoretical, high level. What is governance? In our case, in Polkadot, it's a very specific thing. There is a mechanism, there is a specific logic on chain for handling OpenGov, for voting, for updating your runtimes, for initiating the forkless upgrades. This is something as a dev you need to be potentially aware of if you'll be planning to upgrade your own chain, if you'll be planning to potentially rescue your own chain if something goes wrong. There's an entity you can go to essentially help you mitigate some of the risk where you need very specific help in changing something. And the on-chain treasury, which helps fund initiatives like this PBA. Okay, so this will be a quick bullet list of a few of the core technologies that are actually used in Polkadot. And I think the main one we'll be exploring in the coming days is Substrate. This is the actual framework, the developer framework we built for building blockchains. Substrate is just for building blockchains. This is what it gives you. The blockchains you're actually building were generally we're using runtimes. This is the state transition function, the cookbook. We're being in the form of a WASM, and we're slowly transitioning to a RISC-V alternative with Polkadot VM. There is the governance implementation with OpenGov. This is an actual website I'll be showing you later where you can go and you can vote on stuff, you can make changes. For the authority, this is how we are selecting the validators that get to do all of that. This is nominated proof of stake. This is the solution we are using. For block production, this is who gets to issue the next block. We are using a few different options here. So we have something called BABE, which is the currently used block offering protocol on Polkadot. I'll be explaining exactly what it does in the next lecture, I think today. And we are slowly transitioning to something called Sassafras, which is an improved version of BABE. Most parachains are using a third option called Aura, which is essentially a round-robin block offering, because most of the security is inherited from the relay chain anyway. But for the sake of safekeeping liveness, it would be better if they use something like BABE instead of Aura, because Aura, because it's round-robin, it very clearly tells you who to DOS and potentially prevent liveness. And the actual sharding mechanism that allows all those different shards and parachains to exist together and make sure that we don't re-execute everything is called ELVES, which will show up here in a second. And there is a full-on research paper called Machine ELVES that essentially dives into detail. And I think I will have around 3 hours of lectures explaining the different parts of the ELVES protocol and how exactly we achieve sharding in Polkadot. How do we re-execute stuff to not fully re-execute it, so not everyone does it, so we can scale, but just so we have enough security and confidence. And then we have all of our shard interoperability mechanisms. This is primarily XCM and XCMP. XCM is the language the messages are passed in, and XCMP is the method of passing the messages between parachains. And then finally, we have the finality mechanisms, which is mainly Grandpa. This is giving us the Polkadot finality. And we also have a lighter version of a finality gadget called Beefy, which is used for bridging, which we'll also dive into later. Then we have the scheduling. If we have all of those different parachains, how exactly are we scheduling all this work? When does what get re-executed? Who gets access to this big Polkadot computer we built? And this will be done in Agile Core Time lecture, which I'll be talking about later. And it's not comprehensive. There are some pieces of tech super integral to Polkadot that are not listed here. I think it's impossible to list everything, but I think those are like the most influential ones. Some of the other ones, which I think are at least worth having here if you want to see even more cool stuff, so you can read about it, Google about it, and most of those should be pretty easily Googleable, or I will give you some resources later on. The other ones are, for instance, the database we are using right now, which is RocksDB, or the encoding, which I think you already had some talks about encoding. We use Scale codec. Did you have it yesterday or today? Yeah. Okay. And networking, we now have our own networking implementation called Light P2P. In the past, we used lib P2P. And we have all the API libraries and light clients, Polkadot GS and Polkadot API, aka Puppy, which I think we had people from the Puppy team here yesterday, introducing you to their stuff as well. And actually, there is a 14th element that doesn't even fit on the screen here, which is smart contracts. We have Solidity, we have Ink. Solidity is, well, Solidity, and Ink is a Rust version for smart contracts. So there's many different layers based on where in the stack you want to work in. If you're a networking guy, then you'll be working with Light P2P. If you're some like codec guy, Scale. If you just do database optimization, RocksDB. I am primarily living in this like sharding department here, maybe somewhat connected to XCMP and block production. So I'm living like 3, 4, 5, 6, and there are many different people with expertise in different layers of the stack here. Okay, and so what main actors I will be discussing in all of my lectures? Who are all those, if we have this like Polkadot protocol, which is this big game, who are the players of this game? So there will be 4 main actors that we'll be discussing. First and foremost, we have the validators. And the validators are the relay chain nodes. This is the central element of the protocol. This is when we're discussing the potentially up to 1,000 validators at a time. Those are the guys. They are the general purpose, like super validators that allow all the different parachains to come together and connect. So a validator can re-execute computation from every single parachain. They need to be able to re-execute if they need to. They're like a super node. And they're also the block producers of the relay chain. So not only they can re-execute parachains, but they also execute the relay chain blocks, which aggregates all the parachains. So there is a sub-flavor of a validator that is worth mentioning here, because validators are a pretty wide set. But at a single point in time, which I already mentioned before, we select an active set of validators. This will be explained in detail in the next lecture about staking. But usually when I will be talking about a validator, what I mean is an active validator that was currently elected to be validating the relay chain. Another crucial actor that I will be talking a lot about is collators, aka sequencers, for those more familiar with the Ethereum terms. And their nodes specialize in supporting their own little parachain, their own little rollup. This is a sub-network of the whole ecosystem. They don't have to be able to re-execute what other parachains are doing. Their only concern is their own business logic. And their main job is managing the state of a parachain, managing the state of this small little subnetwork, gathering transactions coming from users of that subnetwork, packing them into blocks we are calling collations. They are collating the transactions and sending those over to the relay chain for an auditing scheme. And just to be clear, both validators and collators here are literal physical nodes. They are not like magical entities or just wallets. They're physical hardware nodes running stuff. And they're distinct. If you are a validator, you're probably not a collator. They're usually quite separate. And nominators, on the other hand, are a bit more ephemeral. They're not physical hardware nodes. They're just people holding some tokens. They're wallets. They're entities on chain. This is essentially DOT token holders that are participating in the staking scheme, and they're helping to elect validators. And like a small little trivia, validators are often also nominators, and they just nominate themselves if they have any sort of self-stake. And then finally, this is a bit of a mishmash group to encapsulate all the different other people, which is the users. This is the people submitting the transactions. So some users submit transactions. They go to collators, they collate them, and then collators package them and send to validators. This is like a short flow of how this whole system operates. And for every single lecture, I will try to give at the beginning a disclaimer. Like in this lecture, we'll be talking about validators. In this lecture, we'll be talking about nominators and validators. So we know who are the actors relevant in this specific one. Okay, so the whole plan for the next 2 days is as follows. We have 12 sessions. Right now, we pretty much completed the first one, Polkadot Introduction. Today, we'll be doing the first 6, and tomorrow we are doing those ones. At least this is the plan. Maybe there will be some extra time here and there. Maybe we'll do some other stuff. We will see. So you can also, based on this agenda here, if you have any specific questions, you can at least kind of see where this question might potentially be answered. So if you can't wait, still ask it, sure, but at least you will have some kind of an idea. And this lecture was a bit more high level, like the idea, the values, the tenets. Most of the other lectures will be a bit more specific, exactly implementation details, how is it done in Polkadot, how are we achieving some of that stuff, and going to the details of the actual protocol of how it scales and how it does all of that stuff. Okay, any questions so far? Question? Where's the mic?
Hi, Luca here. Maybe it's early, but what is incentive for nominator to do anything instead of just nominating himself, like for the validators? What's the incentive?
It is literally the next lecture.
Ah, okay.
Like it will be in the state. Like if it was like, the seventh one, I would answer, but it's 10 minutes, from now on or something. Any other questions? And while the mic is getting there. So why are we learning all of that protocol stuff? To be honest, some of that might be irrelevant to the exact work you'll be doing. If you're just a smart contract developer and you don't care about anything else, some of this might be unnecessary. But as I said, there's multiple levels and layers in the stack on which you can work on, and it's impossible to predict, at least I cannot predict, in which level of the stack you guys will be working on. And I think there's a lot of value to at least know the different layers and the different levels of the stack. So maybe at one point, if you have to interact with people working on the API libraries, you know who to contact, you know what tools and problems they're trying to solve. If you're trying to do some cross-chain messaging, you at least know this level, this tag, those libraries, and who to contact. So if you are to build successful products and businesses and companies and solutions in Polkadot, I think there's a lot of value in understanding the whole ecosystem and all the different levels in it and how to fully leverage that, because it's not as simple as a one monolithic chain with smart contracts and that's it. There's a lot of moving parts with like CM, with different parachains, with agile core time, with scheduling, all of that. So there is value in having access to all those different aspects, and then you can leverage the ones you actually want. Question?
Hello. So I was wondering, what's the scalability trade-off between Polkadot relay chain sharding and Ethereum execution layer sharding?
So what is the trade-off between the Polkadot relay chain and Ethereum?
Execution layer sharding.
Execution, what execution?
Execution layer sharding. Like, what's the trade-off between the both?
Complicated question. So the big difference is, do you want to compare the Ethereum L2 execution or the Ethereum L1 execution?
I was talking about the L2, Ethereum 2.0.
So the L2, the rollups.
Yeah.
So the main difference is that in Ethereum, rollups for the big chunk of their history were not a first-class citizen. There was still a lot of computation being done on L1, and only now rollups are getting a privileged treatment. They're getting some special place in state for their blobs and stuff like that. They're getting more and more preferential treatment, which is necessary for them to continue developing. So in Polkadot, the way it was built from the beginning was that, no, rollups is all that the relay chain should be doing. It is primarily only there to secure rollups. It's not doing other stuff. Ideally, and this is one of the future lectures, on the Polkadot relay chain, there are no transactions at all. We want this to be completely transactionless. There are no balances being exchanged from A to B, none of that. Because every single time and execution wasted by transferring balances on the relay chain is, one less rollup we can secure. And Ethereum is still in this mindset of, oh no, we still have some computation on the L1, but also trying to give this preferential treatment to L2s, and it's like trying to blend both of those. And L2s were not there from the beginning. They're essentially an add-on being kind of patched onto this Ethereum protocol. Ethereum protocol wasn't designed to have rollups. They are not native rollups. Polkadot parachains are native, like the whole Polkadot protocol enshrines them and is fully focused around them. And something like a cynical rollup, this is how we have our parachain implementation, is not necessarily possible to implement on Ethereum because it requires some extra rules to be adhered to by the validators that are not currently possible by Ethereum validators. There's more responsibilities that a Polkadot validator has than Ethereum validator. It's not just re-executing smart contracts. So by that, by doing this sort of stuff, we can eliminate some of the downsides of, for instance, optimistic rollups in Ethereum, which they have up to 7-day latency when you bridge from an optimistic rollup back to the L1. In Polkadot, because we use cynical rollups instead, we can bring it down to a matter of seconds, which is not something you can easily do in Ethereum. And if there will be someone that comes up in a second, oh, but you can actually do optimistic withdrawals. Yes, it works for very specific tokens. If there is enough liquidity, it doesn't work for generic contract calls. If that hopefully answers your question. Another question, and we'll get to you as well.
My question is, are BABE and Sassafras leader election algorithms themselves, or do they come with additional leader election, mechanisms?
So BABE and Sassafras are essentially the gadgets, pretty well encapsulated modules that gives us the block outring. You can pick one and switch it for a different one, like pick and choose. You could very easily implement BABE and Sassafras and others in different ecosystems as well. They're well-defined protocols. I think the third lecture will be about block production. So hopefully that will give you even more context to learn what they are and how you can implement them in different places. So I will hold your horses for now, and we'll get into that in more detail.
Okay, one more question. It's about, you said some validators can nominate themselves. So do they have to stake twice, or the same stake will be used?
No, they have to, usually, they don't stake the same token twice. No, they will have a separate nominator and again self-nominate. You can technically, I think there is a way to just use self-stake as a validator, so you're not a nominator. But if you look deep into the implementation of the palette, what it actually does is it treats you as a different nominator, nominating yourself. But it's an implementation detail that doesn't really matter. You don't get double benefits by staking twice or anything like that.
Okay. Two questions about security. So we've said that the parachains rely on the relay chain, yeah? So number one, can you kind of tell us or specify some of the parameters, security parameters that the relay chain provides for the parachains? And then number two, say we have a bug in the security logic from the relay chain. So what are the strategies that you guys have so that the other parachains don't kind of start failing because of that bug?
So that the other parachains don't what? Like the rust?
Start failing. Let's just say they're not affected by that bug from the relay chain.
There is very, very little a parachain can do to block the relay chain. There are very heavy guardrails to what a parachain can do. They're just submitting parachain blocks for re-execution. And they're heavily bounded to how much execution they can have, and they're heavily bounded by how much I/O they can have. On top of that, they can submit XCM messages. Maybe there are some tags that you try and spam too many XM messages, stuff like that. There are also some guardrails to prevent that, some load balancing to essentially ramps up the fees the more messages there are, stuff like that. When it comes to giving you some more specific guarantees of what type of security and exactly how that works for what relay chain gives to the parachain, I think lecture number when we'll be talking about, where was it? When we'll be talking about state sharding and then execution sharding, I think most of the what exact security we are getting will be describing data availability and execution sharding. So the short story is there are two guarantees. The relay chain is providing data availability, aka some of the state changes your parachain makes are saved in this decentralized data lake held by all the validators for 24 hours. This is one of the guarantees you are getting from the relay chain. The second guarantee is that based on that state in the data lake, which is essentially the inputs to your state transition, the state transition is legal based on your runtime. Up to a certain degree. There are essentially a subset of validator nodes, usually I think it's around 30, that re-executed, re-evaluated your state transition and deemed it legal. So you're getting a confirmation of your state transition. You're getting data availability for the data necessary to perform your state transition if you need to recover it, if someone is potentially trying to withhold this data. And you also get the finality from the grandpa mechanism on the relay chain, because if a relay chain block gets finalized, it by proxy finalizes all the parachain blocks contained or referenced in it. So I would say those are like the main guarantees or the properties you're inheriting. But this will be slowly explored in all of the upcoming lectures. More questions?
I'm not sure like to be covered or not, but if it will be covered like in depth, I'm happy like to wait. One question is kind of like a follow-up question to her question. I was asking about the attack vector that a parachain can expect from another parachain, because the cross-chain messaging is allowed by default. So what do I have to do is a security auditor or as a parachain, like the runtime developer to protect my network? This is the first one. And the second one is, what do inactive validator set do while they are like nothing to do, like they are do nothing?
Okay, so the active validator set. So how we go from all validators to the active set of validators will be answered in the second staking lecture. Second lecture, which is staking, which is right after this one, after the coffee break. The non-active validators don't do much. They just wait their turn. What these active validators are doing is a lot of stuff.
Inactive
validators are not doing much. They're simply waiting for their turn to start doing stuff. So, I mean, they are doing stuff, but they're not really, they're just silently following the chain. They realize that they're not active right now. They are not issuing statements and messages. They're not actively participating in the protocol, but they're still fetching and importing blocks and slowly following, waiting for the moment they become active again, which can happen every 24 hours. And what was your first question? Because there were two.
The attack vector.
Okay, I remember the parachain ones. So the question was pretty much, what sorts of guarantees are we getting from different parachains if you want to interoperate with them? That's a complicated one, because what you are getting is on the relay chain, you have the runtime of all the runtimes of all parachains are registered on the relay chain. So you can easily inspect their individual cookbooks, their state transition functions. So you can look into them and know what they're capable of. You can inspect what can be done there, what can be called there externally, what is exposed as an API essentially. But you have no guarantees, because they're a separate parachain, that those APIs remain active in the future. If they're a separate sovereign chain, they might as well use governance to, I don't know, stall operations, they pause themselves, they change APIs. They're a sovereign chain. Like, you can see what they have right now, and you can be certain that whatever they have there right now will be legally executed, and you can call it. But essentially, you cannot depend on it out of the box for the future. Like, there's no way to guarantee that this company or this ecosystem that's running that parachain will exist in the future, but it's an inherent nature of everything. Hopefully they operate. You can inspect how decentralized they are, you can estimate how likely it is they will be running, but there is always a certain risk of things going bust on every single level. So there is some risk.
I'm sorry, just like let's assume I have my own parachain. How can I protect myself from other like parachains not to harm me? Because like I'm if do I have to like kind of close as much as I can just to protect my
You don't
parachain?
have to actively protect yourself from other parachains. There is not much they can do. You are getting audited by the relay chain, and the only way for other parachains to interact with you is to they can send XCM messages to you. If your runtime is simply ignoring XCM messages, that's it. Like it's up to your destination chain to interpret the incoming messages and consume them. You can simply discard them, and that's it. Let's say it's more like counterparty risk if you depend on a different parachain for your functionality. But this risk comes with benefits. You're offloading some of your duties to someone else, and there's a lot of magic that happens when people specialize, when parachains specialize. Codependency is dangerous, but it is very efficient. And people have to play around with this risk to build complex systems. Any more questions?
Hi, Krishna here. So under core technologies, we mentioned Aura under block production. So is like Aura still being used for block production, or?
So yes and no. But the relay chain, which is where the block production mechanism really matters, is not using Aura. Individual parachains, there are sovereign networks, like it's up to them, are often using Aura as like a simple offering mechanism. The only downside of using Aura for a parachain is that it makes it more easily dosable, this specific parachain. So the liveness guarantees are weaker. In practice, how many DOS attacks we are getting? Not many, but it's always good to prepare. So ideally, a parachain would use something different than Aura. But even if there is a DOS attack and there is a liveness issue, it's temporary and it's probably costly to do it, at least to some degree. But I think there are some parachains that, most parachains use Aura. There are some that don't, but it's not as difficult to not use it, but people didn't really want to switch. It's at least some effort to switch. So yeah, it is kind of used in production, but for parachains only.
Yeah, and just a follow-up question. So when we say like round robin being happening there, so is the round robin for collators being selected in the parachains for block production, or is it like a communication happening or synchronization happening between different parachains? Those are like using Aura, and they are like possibly like coordinating among themselves to like produce the block.
So each parachain has separate collator networks. That means if you're running a node, you're probably collating for a specific parachain. You're holding this, because one of the reasons is if you're a collator for a network, your responsibility is not only to produce like the next block and do the execution. Your responsibility is to hold the state of the parachain. This is why it's kind of impossible for all the nodes to hold all the state, and this is why we sharded. This is why we separated. So the collator is only responsible for holding the state of their own parachain. And how many collators there are for that specific parachain is not the Polkadot's protocol decision. This is up to the individual parachain. There are parachains with like a single collator. There are parachains with a permissioned collator network. There are parachains with many collators. There are parachains with an open collator protocol where there is not even an Aura. Anyone can submit their block, also can work. There are collator networks with very well incentivized decentralized networks of collators. A lot of variety here.
So for current situation, Aura we can consider it's just a function of the parachain and not the relay chain.
Go again with the question.
So like we would consider that Aura being laid or used in silos for different parachains, right?
I don't think I fully understood the
Okay,
question.
maybe
If
we
you
can take it afterwards. Yeah.
Yeah. If you can come up to me after the lecture, we can discuss in detail and then maybe paraphrase and I'll get it there.
Hi, Carlos here. On all the tech stack that you showed, where is the bottleneck?
Where is what?
The bottleneck. Where is the bottleneck? What's
bottleneck?
Bottleneck, yes.
Where is the bottleneck? Right.
Yes.
Okay. I think there are many different bottlenecks, dependent on what we are trying to scale exactly. So it will load in a second, but I think there are some noticeable bottlenecks on the networking layer. And this is why we're switching from libp2p to lightp2p, where we're having our own dedicated networking stack, where libp2p was just an external one. We want to have something that specifically tailors to what we need. And hopefully that will eliminate some of the bottlenecks. I think, for instance, Grandpa is creating a pretty heavy bottleneck when it comes to Grandpa is the part that defines how many Byzantine nodes we can tolerate. Polkadot tolerates up to 1/3 of malicious nodes, and this number specifically comes from the Grandpa implementation. Other parts of the stack could actually tolerate a bit more. Grandpa is the most sensitive one. And because of Grandpa being important and being the most sensitive one, it essentially makes it so even in other more resilient parts of the stack, we also assume that we can tolerate up to 1/3 because Grandpa will break anyway. So this is, let's say, one sort of the bottleneck. There will be some bottlenecks in how elves, this is the essentially cynical rollup implementation, but I don't think they're as well defined. From there, we'll be getting bottlenecks, for instance, how many parachains we can have in the whole network. Because there is a certain, even though we are trying to limit how much re-execution we are doing, there is still a certain number of re-executes you have to do to verify correctness. And this specific number is coming from the elves implementation. So this is what's limiting how many parachains we can have, another bottleneck. I think literally most of those here have some type of a bottleneck that essentially defines some number in this whole protocol. Either the Byzantine threshold, the number of parachains we can tolerate, and stuff like that. All of those are just different implementation details and implementation bottlenecks that exist. Yeah, hopefully that's partially answers the question. Another one, I think we have 5 more minutes until the coffee break, and then we'll just take some time.
So my question was, why do you have an active validator set? Why not choose all of the validators?
Very good question. I think I will be answering that partially in the staking lecture, but generally speaking, networking. This is where the networking bottleneck comes into play. There is a lot of messages and signed statements being exchanged between validators. And if there are cases where a message has to be gossiped or exchanged between every single validator, if you would get to 1 million validators, this just scales quadratically or even worse, and it doesn't really work out. So we, through some simulations and calculations, essentially came up that with around 1,000 validators, our networking stack still holds well. So this limit simply comes from just networking giving up on higher numbers. And we don't, just to be clear, what truly matters here is not necessarily how many validators we are, but what we'll be exploring in the staking lecture is that each of those validators, how much stake is backing them. It seems like, oh, 1,000 validators is not that many, but our stake usage, how efficient with that is super, super high. So there's a lot of stake backing those 1,000 validators at a single point in time. And every 24 hours, they change around and rotate, and nominators adapt, stuff like that.
So just to follow up on that, so let's say like computation power increases over time, like computers become cheaper. So what would be like Moore's law? So what would be your contingency plan in case like computers become more accessible? Because networking is the bottleneck, execution time and like computation is not. So tomorrow, like 2,000, 3,000 validators, like people have actual computers that can run the node. So in that case, would you keep the scale of the execution power required to that time, or would you keep it constant as this, but select like specific validators from that set then?
So from the hardware point of view, the actual limitation nowadays is not the computation. The limitation is the bandwidth. We are much more concerned with the bandwidth that is not scaling to what we need than the strength of the computers. And if we scale to more than 1,000 validators or anything like that at a time, the speed of computers barely matters here. We need much, much, much better bandwidth. But the problem is if we increase the bandwidth expectations for validators, this essentially limits where a validator can be deployed, because you cannot deploy a validator in a rural part of the world where the bandwidth is not up to speed. So if magically the bandwidth and internet access would drastically increase everywhere around the world, then yeah, we could have more validators, but it's mostly about the bandwidth, not the hardware computation. Yep, we can, how much time do we have? 1 second. One more question and then we are done. But maybe
someone else?
We can discuss this topic further after, at the break or coffee break, and let's give one more opportunity for a question and then we are for a coffee break.
Hey, Emi here. So if I want to build my own parachain, I have to set up my own node. What about the collators? I have to bring the collators too with my new created parachain, or the way that Polkadot provides it?
So the short answer is yes, you would have to create them and like properly take care of them. But we are having some new tools being built in the ecosystem, which I will be showing off later. The main one is called PDP, Polkadot Deployment Portal, which is essentially doing that for you. It's this one-click deployment for parachains, where Parity is essentially instantiating some collators and RPCs for you. Is it safe for prod? No, like we are maintaining them. Ideally, this is just a dev step, and then you can, take control of the RPCs for now and then build a proper solution. But it's just so you can start with something and then slowly retake control of every little step. And ideally, after you retake control, you can give the control back to the community of whatever you're building. But if you'll be deploying something, I would say that the best way right now is to just go with something like PDP, which will be available very, very, very soon. And I think it's like in a beta version right now, which will give you like a template from you can start. Ideally, yes. I mean, if you would spin it up on your local machine or something, it's still centralized, but then you also have the bandwidth and the headache of maintaining that locally, or maybe you are doing the instance in cloud or something like that. With the PDP, this is someone else doing it for you temporarily before you properly spin it up in a more decentralized fashion. Yeah. Yeah, ideally you start with something like PDP and then build an incentive scheme so collators are decentralized.